Good afternoon, everybody. We'll give it a few minutes as folks jump on. Bart, it looks like you're out there. If you can hear me, let me know if you have the ability to share your screen, and thanks for being here to present today.
Yeah, I'm here. Looks like I do. It's showing the share screen option. So can I put that up now or?
Feel free anytime.
Okie dokie.
And it looks like Adam just jumped on. He'll do a brief intro and business and hand it over to you shortly.
Okay, sounds good. Bear with me here. I hope this works. Can everybody see my screen okay?
Sure can.
Yep.
All right. So how's the weather out in your neck of the woods?
40 and damp this week.
Yeah, it's about the same here in Michigan.
What part of Michigan are you in, Bart?
Kalamazoo.
Excellent.
Yep, it does exist.
I've been.
Oh, okay. I was out in Hawaii doing some trainings, and the engineer I was with, he goes, "Kalamazoo really exists?" I go, "Yep, just like the M&Ms."
Well, Adam, we're at 29 of participants of 39 registrants, so we can give it a few minutes, but feel free to jump in as you like.
Dan, can you hear me?
Sure can, Adam. Sounds like you're on the road. Maybe.
I am standing at my desk, but I had my mask on, so that probably muted things. Thanks for getting things started. I was coming from another meeting. If we're still looking about the same number of participants, let's give everybody a couple more minutes to sign on. But while they do, just want to say hello from the Iowa chapter and thank you for joining us today. Really looking forward to learning a little bit more about hydronic balancing. I think this will be a good topic to follow up with our airside balancing meeting from earlier this chapter year. Very excited to get into it. Not really much going on at a chapter level for our members to talk about. We are looking forward to a presidential visit in April, so that'll be our society president, President Gullidge, doing a presentation based on his presidential theme, and also a DL discussion. He's also a DL. He'll be doing a discussion and PDH-worthy presentation on what could go wrong with building design, maintenance, and engineering decisions. So if you were at CRC, the virtual CRC last fall, and got to see the same presentation, you'll already know, but hopefully it's new for most of our chapter, and we can benefit from having the society president come and speak to us. That is April 27th, I believe, but keep an eye out for updated information. Same time of April, we will be joining our Green Bay, Northeast Wisconsin regional members and doing CRC 2021. That is a hybrid event, so if you want to attend any of that virtually, that option is available. If you're interested in going in person, also an opportunity to do that. If we look towards that calendar, I think we'll get that sent out and shared with everyone as well from the chapter level, but something to keep an eye out for. There will be learning opportunities in the form of technical sessions. And if you're on the board, then of course there are always business meetings to attend. So keep an eye out for that. And then the final announcement for the chapter is we are gearing up for Des Moines Golf and Country Club for our spring golf outing, and that will take place in May. So I think we're finalizing details on that right now, and the flyer for that should go out shortly. If you're interested in sponsoring the event, get in touch with Nick or Jaden, our RP chairs, as they are handling the sponsorships this year. So I think with that, let's jump in. Thanks for joining us, everybody.
Is that my cue?
You got it. You got it, Bart. And
Okay.
if there's questions, folks, feel free to put them in the chat, unless Bart, you're comfortable with individuals unmuting and chiming in.
Oh, absolutely. Yeah. Because I won't be able to see that unless somebody actually does. So if you guys have questions, definitely chime in and I will address them as we go along.
Sounds great. Thank you, Bart. Take it away.
Okay. I appreciate everybody's time today and inviting me to do this. You know, we talked about what we wanted to do, and I thought maybe a broad stroke would be a great starting point. This PowerPoint really constitutes probably 4 or 5 hours worth of material to go over. So I am available to do lunch and learns and what have you, break this down into smaller pieces, but I call it saving time and improving the results with correct hydronic balancing, because there's a number of principles that we look at. You know, calculations, balancing devices, you know, we hear pick these quite often out in the field, you know, but, you know, we look at stabilizing the system. I'm going to talk about partial loads, you know, because a lot of times when buildings get put up, you know, we kind of look at just one condition, and that's design. And then, you know, kind of breaking this down into pieces. Another thing we'll briefly go over is maybe a tab report, you know, because those become important as well, you know, as a building progresses, you know, where did I start? You know, what can I look at to reference, you know, a changing building's conditions? So I like to start off with balancing because it's basic in principle, but I think it's missed overall. And, you know, these building owners, you know, really look for modularity. You know, they want, you know, something they can change with over time. So if we look at balancing principles, we look at, you know, a strategic approach to balancing. You know, I'll start Down here at my pump, I'll place a manual balancing device, and I just kind of start to follow my flows, and I start placing balancing valves on my terminal units. Now I come to a bifurcation zone and I need to decide which way to go. And there's not a lot of information here. So, maybe I'll place a partner valve here. And, I know there's a lot of people on the call, but can somebody chime in? Why do we balance? What's the purpose behind it? And what does a balancing valve do? Don't we create a little bit of resistance in the system in order to force the flows out to those furthest remote locations? That's the idea. But by placing a partner valve here, we create these little modules, right? But I'm creating resistance here in order to force it out. So with that, I come up here and I go, well, which way do I go now? Sorry, guys. Kids are homeschooling today. So which way do I go here? Well, I don't have information, but if all of these to the right were all 1 GPM, maybe, and these four to the left were all 100, maybe I would go this way, but we don't know. So I look at volume, I'll place a partner valve here, and I'll just continue to go. Once I'm done, I can go back in and look at these modules that I created, based on those partner valves, and then start placing balancing devices in here and continue on throughout the system. And by doing this, I create a very strategic way of balancing this to assure that I get design conditions, and I have a very modular approach further on down the line for the building owner to make changes as the conditions of the building are affected. So when we start looking at this, we follow our flows, we place partner valves where it makes sense, but this also gives me an opportunity to, look at my pump head, optimize it based on design conditions, right? And then use that pump also using a proportional method to balance, thus increasing the operational savings as well. But we need to look at, that concept, we have information from our drawings, pipe length, we know the pressure drop across our devices. Once we have that, I can use my CV equation to calculate a setting on the balancing device that I use. So I start looking at these individual losses on each one of these circuits, right? Going out, including my pipe loss. And once I have that, I can place my balancing device to calculate a minimum pressure drop per se, if these are all created equal across for measuring purposes. And once I do that, I can calculate my total pump head. Once I have my total pump head, I can go through and calculate the loss at each one of those locations, thus using my CV equation at this point to calculate an opening, reducing the amount of time I spend balancing a building and improving the accuracy of it. Any questions on that? I guess the next step, once we look at design conditions, would be looking at, differential pressure within my system or ways of stabilizing it. And if we start by looking at my heating and cooling season, and the fact that we're rarely in design conditions, we're typically in partial loads. So if I look at that in my heating season, that becomes at 50% load, that becomes 58% of the time. My cooling season, 68% of the time, again, that we're in partial load. And if I look at a typical heat exchanger or terminal unit at 50% load, I'm at 20% flow. Rarely are we in design conditions at 100% flow, 100% of the energy that I require for that space. Now, if I look at this flow, and this one becomes really important, using the relationship that my delta P is proportional to my flow squared, at 20% flow, I'm only taking a 4% loss in my pipe. And the analogy that I like to use is, imagine everybody on this call, has a piece of garden hose and it's open on the end. And I go to the wall and I turn on the faucet and water starts coming out. What condition would that be? Maybe design. But let's say half the group takes their thumb and they stick it over the end of the hose to depict partial loads, 20% flow. Now, what would happen to the rest of the people on this call? Well, because I'm only taking 4% loss, my faucet is my pump, then everybody else would be getting a little bit more flow. And let's say that of that group, half of them just put their thumb right over the end of the hose because they're satisfied in that space. Because what we're getting is called interactivity. And because of the lack of pipe pressure drop in my system, and depending on where my pump's going, the flow requirements at each one of those terminal units, that becomes some of the issues that we look at as far as why we want to stabilize a system so that we can identify partial loads and maintain good control valve authority. Because if we look at a typical control loop, we're in a room, we create a disturbance, our body heat, laptops, projectors, whatever the case may be. That goes back to my sensor. I look at the deviation from my set value, plus or minus 2 degrees, however it's set up. Based on that, my controller will put out a signal to my actuator, creating some type of lift or extension. That's the easy part to calculate. What I don't know is, depending on the position of everything else in my pump, what kind of pressure drop am I seeing across my control valve? So how does this lift equate to my flow to my terminal unit, creating that power output that I require to satisfy that disturbance? Now, we've already established on a typical terminal unit at 50% power output, I'm at 20% flow. Now, if I look at a two-way EQM characterized control valve at 20% flow, I'm at 50% lift. Now, if you notice, those two curves are opposite each other. Excuse me. Now, there's a couple other things that we would include in this calculation: control valve authority, the characteristic of my actuator. Okay, but if I take these two curves and notice they're opposite, and I look at power output to lift ratio, we end up with this. This is what an engineer designs to. This is what a building owner expects. If he gets 50% lift, he wants 50% of what he's looking for. Now, this curve here on my terminal is rarely going to change. Okay, but the one I'm really worried about is this one, my two-way EQM characterized control valve. Okay, because depending on the pressure drop across my system, how does this curve change? And then how do I ride that curve to maintain this output? And how we do that is simply by looking at the control valve authority, beta. So when a system gets designed and the control valves are selected, we know this, it's constant, right? The valve's wide open, design conditions. But what I don't know, because it is a variable flow system, let's say this one down here is at 20%, the one above it's at 50%, and so forth throughout it, right? Or maybe this is a district loop. We're on a hospital or a campus university project, and my central plant, and these all indicate buildings. And this one's at 20, and this one's at 50. Maybe this building's completely satisfied, and this one's at 30%. If I start to close off a control valve, what do I create? Maybe additional pressure drop from what I calculated. So what happens is we get what's called interactivity within the building or within my campus energy projects, right? I add a new building, right? Maybe additional pump head. And depending on the conditions of these buildings, we'll get interactivity between buildings as well. So this becomes my variable. It's constantly changing. Because if I'm going to calculate, a design authority, I would look at my delta P of my valve wide open divided by my delta H of that circuit versus my minimum authority would be the delta P of my valve wide open, and then whatever available pump head at that particular moment in time during the operation of that building, to figure my minimum authority. So the importance of stabilizing a building become extremely important, because we want to maintain the controllability we're looking at. We don't want to have the delta T issues associated with it, right? So we balance our building, we stabilize it because of partial loads, because we're rarely in design conditions. So we use some kind of stabilization or DP control device to stabilize, let's say, this floor or this building to what's called an index. So whatever the highest demand is on this floor or building, I would calculate that, determine that's my index, and that there's not too much difference in between. So if I had 3 PSI, 3 PSI, 3 PSI, 3 PSI, this would be my index, plus the pipe is what I would use a DP controller to stabilize that floor. And by doing that, any of the interactivity from the rest of the building is reduced because I'm stabilizing this to whatever this design condition is, so that I maintain good controllability or good minimum authority. So I don't fall below the minimum of 0.25. Does that make sense? Okay, so there's a number of ways that we look at, balancing is important. Partial loads become important. But in order to achieve this, we have to do some calculations. Now, sometimes we look at devices that we can use at a specific location. And, maybe we look at a specific, terminal unit as far as controllability, which gives me a pick fee option, right? And, we look at a device like this being used quite frequently, over the past few years. And they're great solutions. I never look at anything as a one size fits all, because when an engineer is designing a building or a building owner has a specific requirement, I really look at everything more like a prototype. What is going to be the best solution for that particular building? So I might look at a pick fee, but I will also look at its function. I will look at, what its capabilities are based on, the available pump head within the system. Is it, I worked on a project not too long ago, hospital, and they wanted an off-the-shelf pick fee throughout their building. It was on a district loop. They had a central plant, 120 PSI of available head pressure. They had 30-inch pipe on their distribution, and then they had 12 or 14-inch pipe going into the building. Okay, and I, explained to them that, based on what they wanted to use, it wasn't a good solution. And the committee I was talking to really was asking me why, and I said, because you have to look at what you're going to see at these specific locations in the building, how much available pump head from the from your central plant is going to be available there. And then, is this solution going to work for you based on the capabilities of the valve you're putting in? Long story short, we looked at, something that could handle the pressures that were going to be available in the system. So it becomes important to identify what the capabilities are of the device you're installing. It's not a one size fits all. Is there a combination of stabilization in order to reduce the amount of pressure going into a building, or on a riser that I'm able to use off-the-shelf product in order to get the controllability I'm looking for? So it's important to understand what those capabilities are, what the requirements are of the building. Can somebody tell me how a pick fee works? It's not magic.
to regulate the upstream pressure, so your control valve authority is higher.
Yeah, I guess in general, yeah, that's a good example, right? So I get pressure that comes in, starts your DP portion or your stabilization, so that I maintain a specific pressure drop across the valve, right? In principle, that's exactly what it is. So I get pressure that comes in, right? Now my DP controller is working, so I'm stabilizing. I can make an adjustment now to regulate whatever that design flow should be. And once I'm doing that, I can put an actuator on top, and then the actuator, based on the signal receiving, will control the stem to modulate the flow based on the requirement of that room. It's fairly simple, but I'll say this. I don't care what device you put into a system based on design and requirement, you should always be able to measure and verify, because over time, we all know that oxidation, the conditions of the building change, and we want to make some verification so I can do some diagnostics if there's issue. I don't want to go out there with a left-handed screwdriver and an Allen wrench and start making changes. I want to make smart changes, to reflect the condition of the building. These are great devices to stabilize at a specific location. But I want to make sure that it's going to work based on, what's available in the building, what the parameters of the specific valve are able to handle. So, we're looking again at balancing, stabilization, pick fees, operation of a pick fee, measuring, diagnostics, all of these things come into play. And I say this term, having a building that's modular that I can change over time. There definitely isn't a one size fits all approach. It's important to run the calculations or, do these so that I'm making educated decisions, to supply something that's long-term. One of the other things that is pretty close to my heart is definitely, balance reports, looking at, where am I at on the day I hand this over to the building owner? Because this information becomes really important, let's say 5, 6, 8 years down the road. I can look at, what's installed. I can look at, whatever the balancing device or control, whatever that setting is, what that CV is, what my measured pressure drop is. But most importantly, when I start looking at measured flow versus calculated flow, what is that deviation? And then if there's changes out there, can I measure it and verify what's going on? And then now I can make educated decisions, kind of based on the information that I gather, and make those changes adequately, and maybe reflect where that building is at that particular moment. Any questions on that? This one's kind of short and sweet, guys. It really goes over a few different principles, that we do. It's the idea is to, use the right tool for the right job, or a combination of, right? I don't use a screwdriver to take a bolt off. So it's looking at these and then breaking them down, because realistically in here, we've got key 1, which is, balancing, key 2, which is stabilization, and then key 3, load compatibility. And then in between keys 2 and 3, we do what's called pump optimization, because I get the question quite frequently on, if I'm using a variable speed pump, where do I put my sensor? Do I use multiple? Can I use a polling method? Which is the best way to do it? And we kind of go over all that. And so this PowerPoint really breaks that down into smaller pieces for you. But the whole idea is really to looking at a project, breaking it down into a simpler form, and then running the calculations, entering in however you do yours, is looking at my flow, my pressure drops, my pipe lengths, right? and then coming back with, information that makes sense. Most importantly, looking at my minimum authority and my design authority, my velocities within my system. All this information becomes really important, when you're making decisions on, what devices you want to use. Do I need to stabilize it? Does it make sense? What's my control strategy? Is this a retro where I'm looking at delta T issues? Do I have pressure issues? We really need to look at, the fact that we start at distribution and work our way back to mechanical. We can't do it the other way around. If I can't solve my problems out in distribution, the mechanical room is not going to do it by itself. It's a totality approach that we do this, and we do it smart because, CO2 emissions are becoming more important. Operational costs are definitely, at the top of everybody's mind. And I want the controllability that's kind of required. This one's kind of short, guys. I think we're 30 minutes into it, but it's really meant to be more thought-provoking, looking at the more of a systems approach than a device approach. I hope that this is at least strikes some interest with you. Next time I'm in town, maybe we can do some face-to-face, and break this down into, a more detailed approach to looking at, balancing devices, that strategic approach to, looking at the system, stabilization, looking at delta T's, looking at my minimum, my design authority, and then taking a prototype approach to looking at these buildings. Any comments?
In the world of more efficient control sequences where you've got differential pressure reset, do you see a lot of authority at your typical control valves and what have you that actually support, I guess not overflowing, which would be balancing in a lot of systems? Do you think that's helped a lot of systems, hurt a lot of systems?
Well, I don't know if it's hurt systems, but it's reaction time. You're talking about integrated sensor.
I guess what I'm talking about is just a differential pressure reset control strategy, many times based on valve command.
Well, if you're talking about polling method, unless it is a 100% pick B solution, then it's not ideal to do because of the pressure change across the control valve. In some cases we see where it's on-off control throughout. So I'm opening on 100%, I'm closing 100%. So we don't get an average there, but based on the output signal back to the BMS and then the pump reacting to that, it's not ideal. If I'm using pick fees, then it's what I would do if I was using a polling method would be looking at my index, which is my highest demand, including the pipe from the pump, and then maybe look at a couple different locations. And then on some projects I've worked on, we've actually built diversity into it because they knew they would never need 100% of that design flow. So there's a number of control strategies to look at depending on the project.
Well, Bart, thank you for the presentation that you've given us. Really appreciate that. I'd really like to encourage our members to chime in with some more questions. I think we've got a great starting overview, but
I know it's hard
but to dig in a little bit more, it's definitely more challenging, not in person, but
it is, and I understand, guys. I try to keep these webinars a little bit shorter because it is very difficult for everybody to sit in front of a laptop all day long. And I truly understand that. Hopefully in the near future, when everybody is safe and we're able to do more of these face-to-face meetings. And guys, I do full 1 hour lunch and learns on these different subjects. So, if need be, reach out to Gary with Vitalik, and we can set those up.
Oh, yeah. Yeah, then I had a bunch of emails as well.
We discussed specifically PIC-Vs. Can you go into a little bit more detail about other balancing valve options?
Sure. I mean, there's, you definitely have the manual balancing valve. You have the, circuit setter, which is more of a ball device. And then the automatic balancing valve, and realistically, all three are viable solutions, and I always look at from a standpoint, you have to look at the economics, of a project. And then, what is the building owner looking for? I'll say it till I'm blue in the face. There is no one size fits all. I really take a strategic approach to looking at buildings. And I do run the calculations on what's going to be best. What are they looking for over time? Does any of the space change on a frequent basis? Do they need that flexibility? There's balancing devices, there's PIC-V devices, there's DP controller devices that we look at. For me, a number of the, I'll say university projects and hospital projects that I work on, excuse me, we look at DP controllers on an inlet of a building. And, then I start maybe using PIC-Vs, internal to that. And, so I take a different approach. I'll optimize the central plant to the loop, and then I'll optimize the building based on, devices being installed there. So we really kind of peel the onion back in order to adequately look at these projects, because there's just so much low hanging fruit, on these buildings that are out there, for energy savings, operational cost, pump energy savings, excuse me, become, easy to look at, and then, as I go through my district loop or within my building based on budget, there's an actual return on the investment for the building owner. And that becomes really important, because everybody's looking at cost savings. In my experience, whether it's in steam or hydronics, to look at, PM in a building, where a lot of the building owners I talk to, they're more reactive than proactive, budget cuts, whatever the case may be. So whenever I look at a solution, I try to make it as simple as possible for them to gather the information, make a change. But even that's dynamic. There's so many variables in there. What's the water quality like? That becomes a big player in it. I was on a university project a number of years ago, and the facility guy said, "Hey, we use a boatload of makeup water every year." And I asked him, I said, "Well, where's it going?" He goes, "We don't know. We think we got a leak somewhere." And I just kind of laughed. And it's, it's things like that, I say this tongue in cheek, they're out of our control, but, they're aware there's a problem and they understand they truly have water quality issues, which affect everything installed within that district loop. So we peel that onion back to identify where those problems are, and based on budget, try to come up with solutions. They're going to help the building owner with the problems they're experiencing. Any other questions, guys?
I guess I was just going to make another poke. There's certain individuals out there that'll that'll make the argument, and I'm not necessarily one of those, but it does potentially have some merit in certain situations. The water balancing might not be necessary as long as you've got characterized control valves, a smaller system, and potentially controlling to say like a discharge temperature or something like that.
The only way I would agree with that would be if that CV value is 100% accurate based on the design flow and the available pressure drop at that specific location. Otherwise, you have to have balancing, and that's the dilemma that we see. Don't disagree with you at all on that, and if the CV reflects the design flow required and whatever available pressure drop is there at design condition, mind you, the problem becomes partial loads, how I'm operating my pump. And then because of the interactivity in the system,
So you talk about how you're operating your pump. So energy code basically requires a differential pressure reset unless there's like good reason not to.
Oh, absolutely.
So I'm in the commissioning field, and so differential pressure reset, it's fairly common, but not always specified. And so I was always under the impression that when you have a control sequence like that, that basically pulls your valve commands and says, hey, if I've got a valve somewhere, and this is also for kind of air balancing as well, duct static pressure reset and differential pressure reset kind of work the same way. I've got a valve that's 90% open or more, I need to go ahead and reset my differential pressure, of which my pump controls to, higher. And when my system loads go down and I don't have any valves in my system that are open more than, say 80%, I could go ahead and reduce my differential pressure reset. And so when I reduce my differential pressure set point that I control my pump to, my control valve authority across all of my control valves in my system decreases, right?
Well, it depends, because what if the one that's 90% open that the pump's resetting on is 300 GPM, requires a certain amount of pressure drop across it. And then the other ones out in the system are at 20% open or 30% open. And so my pump ramps up. What happens to the differential across those smaller flows?
Right. So the differential increases, right? So as your DP increases, your control valve authority potentially decreases, especially the ones closest to the pump, right?
Correct.
Your control valve authority decreases. That's where you want to have your balancing at. So when you're talking about kind of having your intermediate balancing valves, I mean, closest to the pump are the ones that you probably have the most issue with from a control valve standpoint, and the ones that probably need the most, I guess, cranking down from a balancing standpoint are closing.
Yeah, but here's
right.
Yeah, but here's a different solution. Okay, let's say we don't use balancing. Okay, I'm not disagreeing with you, but there's some parameters in there that I would have to be assured happen, and that would be the correct CV based on available pressure drop at design conditions within that building. Second, I would look at using some kind of DP control device, maybe on those floors, to stop any type of interactivity. Then I would have an ideal solution where I wouldn't use balancing.
Yeah, I think those intermediate control devices, like on big branches or on certain floors, I think those are definitely a good solution in large systems.
Yep.
And potentially necessary.
Yeah. So I mean, I'm not in a disagreement, and I think we're right there. It's just so important, to look at the calculations that we do, and then identify the correct CV requirement, because so often than not, with a lot of the engineers I work with, across North America, you look at a specification and it might say 3 to 5 PSI. Okay. And then maybe there's a CV there, maybe there's not, but there's definitely a design flow based on, devices selected, and this is where I take a harder look at what's going on during partial loads and run those calculations to determine what is going to be my minimum authority, based on the position of my pump at that time. And those are some approximations. because even when I do my lunch and learn based on pump optimization, we kind of break it down, because in a lot of cases you can see systems, depending on sensor placement, depending on my set value, where we get underflow and overpressurization within the same building. So it's really kind of I'm glad you brought it up, because it's really kind of an interesting conversation that, we could probably spend a few hours talking about.
Well, I guess I hear PIC valves a lot, and I guess admittedly, I'm not really sold on PIC valves. They might have their applications, but I don't think I'd ever put PIC valves in an entire building, because you've got so many more things that you can do.
Yeah, right. See, I take this, and that's the approach that should be taken. It's not a one size fits all, because if I could use a DP controller device and then have the absolute correct CV at some locations, but then maybe I have some offices, maybe some bigger air handling units, that might be where I use a PIC V. Use more of a hybrid approach than a one size fits all.
Could I jump in here? I had a question. I was wondering if you had any kind of words of wisdom for how to approach hydronic balancing when you have diversity in the system. Say you've got a pump with, the pump's designed for 400 GPM. Your total connected load is 500 GPM. You have a typical approach is to open everything up to full flow, and if you're using manual balancing valves, you balance each one to the proper flow.
Mm-hmm.
What if you don't have enough pump for that?
It's weird how often that happens. I have worked on a project like that, and everybody involved went back, built, said, okay, we're going to build diversity into it, reflect this. Well, that's a slippery slope, because again, in this particular case that we did this, we knew that the water quality in the system was fairly bad on this district loop. And for this university, unfortunately, there was a lot of air in the system, a lot of particulates. And that particular building owner had reached out to me about a year and a half after, with a lot of issues, not because of diversity, but because the pump was undersized to reflect changes over time. So it wasn't really built into it. I'm not sure how to answer that adequately.
Don't worry, you're not alone.
Well, it's we work on projects where I have diversity built in one side of the building versus the other one. All my main headers are sized for design flow. Everything on that one side of the building is designed around diversity. And I totally get that. Can you do it during the tab process on a system? Absolutely. And it happens. And sometimes based on what you just said, yeah, I've got to throttle it back a little bit. I suppose there's more people involved at that time because somebody has to sign off on that.
I would share that as a balancer, what we've had success with in the past is not really taking a really hard approach to trying to obtain the design flow at every single element of the system, but to let it control to differential pressure and check potential worst case areas, worst case coils, and verify they can achieve their design flow when it's controlling to the DP set point with somewhat of a load in the building. And that's sort of the tricky part. If you don't actually have a real load in the building, then you have to find some way of
creating it.
Yeah. So yeah, it's a challenge, and just throwing it out there.
No. You know ABC?
ABC.
Oh, okay. Okay. Yeah. I did I spoke at, well, your Canadian national meeting. And a similar question came up. Great organization. I guess, I'm just thinking here. Yeah, I mean, I would agree with you, assuming the previous gentleman's question applied. That, the correct CVs were installed. I'd have to look at at the index within my building in order to, look at my pump sensor placement, look at my set value. And even in that case, I've built diversity into the set value for my pump sensor in some cases, because they knew that it would never get there. So yeah, I suppose I could see that, if your highest loads balance into it, but it's so dynamic, and there's so many variables in there that I would want to run a few calculations in different sections of the building to verify that, I don't have that increased interactivity.
You mentioned correct CVs a lot. I guess what I've seen in a lot of specifications, and I think you've mentioned too, like 3 to 5 PSI of like differential when it comes to just like sizing control valves.
Mm-hmm.
Not really sure exactly what it says for sizing the balancing valves, but I got to assume that's similar. So I guess the question I'm curious about is, I mean, are you saying that in order to do this right, a design engineer has to go through each individual, coil and specify a CV, or can they kind of blanket it like most specs do? And, or if the design engineer doesn't, are you saying that someone else should or does?
I do. Okay, I do. And that's a personal choice. But again, because I've been doing steam and hydronics for as long as I have, it's been, and the guy that taught me, years and years ago, I think he was like 200 or 300 years old. But, it was always calculate, look at the CV, look at the conditions of the building. If you fall below minimum authority, I mean, all these things came into play. So the reason I mentioned correct CV is because, we do look at the 3 to 5 PSI. That's pretty standard across North America. I mean, it's always been like that. And I'm not bashing that at all. All I'm saying though is if you look at a system during design, and you calculate pipe loss to each one of these locations, I look at my pump running at 60 Hertz or whatever range it is in order to meet that design condition on my index, because that's what I'm basing my pump head on, that I'm calculating what available pressure at each one of those locations is, because then I can adequately calculate the CV based on that flow and that pressure drop. And if I do that, then I've got something to work with as far as not using a balancing device for design conditions. Because let's be honest, guys, a balancing device is in there for one condition: design. The control valve should be picking up, controlling my flow based on differential and whatever outlet temperature I'm looking for. And that's the dynamic of the system. And that's, I suppose that's the crutch, is looking at that. And that's kind of why on those previous slides, I emphasized correct CV, minimum authority, design authority, so design, partial loads, and then, what's the math take me to?
Does it make it harder, like, from Matt's standpoint too, as a balancer? So usually the balancer provides the differential pressure set point. So is that something that when you're doing your calculations, you kind of have to like assume? Because I thought I kind of heard you say, well, we kind of do it based on the pump sizing, and admittedly the pumps can be sized a number of different ways. So it's kind of hard to assume exactly what the system's going to do based on the pump. I guess I thought.
Absolutely. All the calculations I do on a system. So if an engineer gives me a drawing or a building owner gives me his as-built, and they are correct, I run through and I do the calculations based on the index, which is the highest demand within that building, including the pipe from the pump. I will calculate the required pump head to the nearest foot. I don't care what's installed. I will calculate it based on the nearest foot. And then based on that information, I'm able to calculate what the set point is, and then that sensor placement. So yeah, I agree with you. I know there's some safety factors built into these systems, especially at pumps. They want to use that pump for, number of years. So when I'm tabbing a building or I'm working with, somebody that's balancing the building, I bring all those calculations with me. I look at the presets. I look at, what I calculated for a pump head, whether it's an automatic balancing device, a manual balancing device, and then we'll ramp that pump down at the index for a starting point. Now I've got something to work with.
I also heard you say sensor placement there. So it sounds like you kind of look and potentially even help guide sensor placement, the differential pressure sensor placement.
Oh, absolutely. That's super important.
Right. And so I would tend to agree. And so I guess the question there is, I was kind of always under the impression that maybe not exactly at, but at least close to your worst hydraulic location is typically a good place.
Sure.
I guess I'm asking for confirmation if that's what you would also recommend, or maybe there's some nuance to that guidance.
Let me think if I have. Oh, I do have. Sorry, guys, I don't have any Muzak to put in the background here. Okay, so if we look at this building here, okay, and I got a standard 2A modulating control valve, I got a balancing device. Let's assume some other stuff's in there as well. I have a pump running at 60 hertz. Where would I put my pump? One sensor, mind you. Where would I put that sensor? I have no idea either, guys, because the idea would be I'd have to know the delta H of each one of these locations, and then the pipe loss all the way back to my pump to figure out which one is going to be my index. Okay. Now, once I identified my index, I've already calculated my delta H at each one of these, right? So when I look at my set value, I would look at the highest delta H and then add 4% to that to figure out what my set value is going to be. Because we have to account for, we have to account for this during partial loads. And even if I'm generous and I had 6%, my set value should reflect, and maybe we go the opposite direction and we build diversity into my set value for my sensor. But it's not always in the same location. And it's important to understand that when I'm calculating, gosh dang it. When I'm calculating sensor placement, that location doesn't always reflect what my set value is going to be. Because if this was my index and I calculated this one, delta H plus pipe loss, my sensor is going to go right here. But let's say this one's delta H is bigger, but the loss to the system doesn't equate to what this one is. So this value here would be my set value. Does that make sense? Because the idea by having that set value is not to starve anything, but still come up to design conditions at my index.
Agreed.
So it's, it's calculations, without a doubt. How we doing on time? Guys, and again, I'm always available to break this out into 1 hour lunch and learns if anybody's interested. Gary, the local Victaulic line sales guy out there, great contact for you guys to reach out to. And we can break this down in smaller pieces. The pump optimization, DP stabilization are extremely popular requests that I get. So definitely available. Do you guys enjoy this?
A couple of us did, I think. No, I think it,
What you meant?
Well, I am very happy that you guys chimed in.
absolutely. Thanks a lot.
I'd like to
You're welcome,
second that. Thank you. Thank you for your
I hope everybody
participation,
enjoyed it.
and Bart, thank you.
Okay, enjoy the rest of your day, guys.
Thanks, Bart.
Thanks.
Thanks everyone for calling in. We'll see you next month.